we move on to manifolds. It's a discussion on manifolds, which is will be a bit more involved than what was there in the first part of the course. And what I will be discussing today, first of all, is the general concept of tangent and dual vectors. Then we'll go on to discuss derivatives in a little bit more detail, and finally symmetries of Riemannian manifolds. This can also be generalized to the space-time or pseudo-Riemannian manifolds that you'll find in general relativity, for example. But let's start from the beginning. So the first thing we'll discuss vectors. So in particular, tangent vectors. So you'll remember how if we have a Euclidean space, we can define a set of basis vectors as EA being just the derivatives with respect to the coordinates of the position vector, right? However, in the general manifold, we might not be able to do this because we will simply not have access to what is a position vector. For example, you can imagine a sphere. There is no actual position vector on the sphere. There is no vector inside the sphere that points from an origin in the sphere to anywhere else, so to say. You cannot add displacements like that on the sphere. So in general, we will not have access to a position vector like this. We also can write down a different set of vectors, which is essentially the gradients of the coordinate function. And with those two, you turn out actually to be defining something like this, that this is delta BA, right? So we'll find something similar in a general manifold. But first, let's discuss two different types of vectors. The first type of vector, if you think about what kind of quantities we can describe using vectors, is displacements. You typically think of a vector as a displacement from point A to point B or similar. And for example, if we have a curve like this, you could think of a tangent vector being a small displacement along the curve, and so on and so forth. If we have a curve parameter here, t, let's use that later on. So in this case, for example, you would say that the tangent vector VA would have components which would be, and I'm going to use y as the coordinates, would have these components, dya differential with respect to t. You can also write that as y dot a. So that's one type. And the physical quantities you'll describe using this is velocities, for example, but also multiples of velocities such as momenta and so on. Then we have a different type of vectors. That's vectors describing how something changes, how some function changes. So that would be something like a gradient of a scalar function. And if I take then the components here, the A component would be the partial derivative of phi with respect to the A coordinate. So typical things would be, whatever changes, like if you have a map, the height of the terrain on a map would be a scalar function, and then its derivative would be a gradient vector. And using one of those types of vectors and one of those types of vectors, we could generally find out how this something, this phi, how it would change along this curve. So typically we would have some function here that is a function of position, and then we would have something like we could describe how fast that function changes with the curve parameter t. Then that would be defined as the phi dt, but just by the chain rule for derivatives, this would be dA phi times dya dt, and we recognize these as the components of each type of vector, right? Which is this. So this would be something like this gradient, the A component, and then this tangent A component. So that being said, we should note that there is absolutely no reference to a metric here, and we don't need a reference to a metric in general, because everything I used was just the chain rules of derivatives. And then I split this quantity, this change in the quantity, into something that we recognize as covariant components, and something that we recognize as contravariant components, and each belong to different type of vector essentially. So that being said, the first thing I want to discuss is displacement. So essentially this first type of vector we're going to see there. Okay. So as I said, in the general space we don't have access to this position vector. So what are we going to do instead? Well, if we look at this expression with the position vector, and then we think about what was it that made this expression have the correct transformation properties? Well, it was not x. X is an invariant object somehow. It was this partial derivative that essentially gives you the full transformation properties. So it gives you the different. It gives you how different basis vectors relate to each other, right? So that is actually what we're going to use. We're going to see, so this is the definition of tangent vectors. Tangent. Those are linear combinations of partial derivatives. So instead of writing this down, since we don't have access to a position vector anymore, we'll just drop it for the time being. So we essentially write that EA, we define it to be this partial derivative. And in a sense, it's natural, because if you write down the prime vectors, that would be the prime derivatives. And again, if you use the chain rule for derivatives here, you would have dya, dy prime, a prime, dA, right? So this thing here is nothing but EA itself. So indeed, you get the correct relationship between the basis vectors. You get exactly the same as you would have in Euclidean space. So all of that came from the partial derivative. It did not come from the position vector that we don't have access to anymore. And we'll see how this also makes sense in a way, because it's exactly this, right? We wanted to have a tangent vector of a curve here, for example, and that should have these types of components. And And it's exactly that which comes out if you do this. So this will have exactly this expression in any type of coordinate system that you write down. And so you can write down the change in a function phi essentially as this linear combination of partial derivatives acting on phi. And we'll write that essentially as v acting on f, well, phi. I used phi, so let's keep it to that. That would be VA dA phi, right? Okay, so that's the tangent vectors, and this would then be equal to, for this tangent vector, it would be equal to this phi, which is just d phi dt. So this is you can view the set of tangent vectors as essentially directional derivatives of scalar functions. Right. Any questions? And you'll see also that, I mean, you can make linear combinations of those as well. A linear combination of partial derivatives will give you a new direction derivatives. Okay, so just to mention here, so the set of linear combinations of partial derivatives at the point P is denoted as TPM, and the different constituencies is that this is just saying the tangent vectors, the point P at which the tangent vectors exist, and M here being the underlying manifold or space. When we say manifold, we essentially just mean a continuous space. There is a map of coordinates of local coordinate system that is a one-to-one map to continuous differentiable map to some subset of Rn in Euclidean space. So for example, the sphere S2, so you know what the sphere is this set of points. For example, in this point, if this is the point Q, then the tangent vectors would be essentially a linear combination of all. It would be any linear combination of partial derivatives at the point Q. So these that are tangent to the sphere. So this would be the tangent set of the sphere at the point Q. And you'll also see that if we go to a different point here, let's call this point P, this has a different set of it's a different tangent space. So a priori, these vectors do not live in the same vector spaces as these vectors. They are different vector spaces. So partial derivatives at a particular point form a vector space. You can't add a vector from this tangent space to a vector in this tangent space, in general. Okay, so that about that. Those are displacements, and you'll notice also that without any reference to a metric, there is no natural map from taking two vectors here, two tangent vectors, and mapping them to a real number. In order to do that, we will have to introduce some sort of function that takes two vectors and maps them to a number. Of course, if you think about the sphere, you will think about the sphere embedded in some three-dimensional space, and then that will itself induce a metric on the sphere that will take two vectors and map to a number, and then you will have a metric. But for now, let's just remember that you don't need to have a metric in a general manifold. I will discuss an example a little bit later on that. So this was the first type of vectors, right? So this was the vectors describing displacement. Those are the vectors that we describe using these partial derivatives. Then there's a mathematical construction for any vector space, really, but in particular for this, we have a dual vector space. So for any vector space V, the dual space is defined as the set of linear maps from V to, well, let's assume we have a real vector space, then it's a map from V to R. And this itself forms a vector space that is called the dual space. And you can see that it is indeed a vector space with a natural definition of additions, for example. So in particular, let me just add here, this is typically denoted V star. In particular, the dual of the tangent space here, TPM, is denoted T star PM. So essentially what we're saying here is that if we take a vector, any vector that is an element of the tangent space, and we take an element, what did I call it here? I call it W. W, that is an element in the dual space. Then the following should be true. Then W, that's a map from TPM to real numbers. So essentially we can take the function W and map V to a real number. But we can also write V in terms of its components. So this would be W, VA, and we had the basis DA, right? But by definition, it's a linear map. The dual space is a set of linear maps, so we can use that to take these components outside. This would be VA, W of DA, and this I'm just going to define as the component of W. And then all of this is equal to VA, WA. So far I have not discussed what the basis is here. So what basis do I use to express this W with this component? But we'll see that in a short while. And this reminds us of an inner product, right? It reminds us of what we had in Euclidean space. We have the components of V summed with the components of W. The difference to an inner product here is that V and W here are elements of different vector spaces. One is the vector space of tangent vectors, and the other is the vector space of linear maps from tangent vectors. And without having a metric, we can't actually make this into an inner product. We can't relate W necessarily directly to a particular vector V. Okay, but this is exactly the type of thing that appeared here, right? For example, if we wanted to describe the change in phi, a function on this space along a curve with the curve parameter, this is exactly what we used. It's exactly what we had. We had a tangent vector with its components, and we had the gradient with its components. Okay. So this somehow reminds us of the inner product without actually being an inner product. So as I said, we've now expressed some sort of components here, but we would like to know what is the basis corresponding to these components. I mean, we saw that the basis here in the tangent space were the partial derivatives. So let's see what the basis is here, the kind of the objects that we are going to use to express these dual vectors. Okay, so if you think back now to the Euclidean case, we had these dual this dual bases were kind of the gradient of the coordinate functions, and we'll get something similar here. So the first thing we'll do is to define the differential. And so the differential is a dual vector that, given the function f from the space to real numbers, we define a dual vector that we call df. We define that as when it acts, it should be a linear function on vectors, right? So it should take a vector as an argument, and we define that as being the same thing as having the vector acting on f. And you can see that this is indeed going to be linear. It's going to be linear in V, because if we take, for example, V plus U, a linear combination of two partial derivatives, then this is going to be V of f plus U of f, which by definition here is the f acting on U plus the f acting on V, which is the f acting on U plus V. So that's fine. This is indeed linear. Yes, please. Yes, you have to think about the linear mapping from tangent vectors to real numbers. That's the definition of a dual vector. Because that's the definition of the dual space, right? So we define the dual space here as the dual of the tangent vectors. So it's a linear map from the tangent space to real numbers. Okay. So, but if we write this down here, let me continue. Let me remove this for the time being. And let's continue here. We saw that this was equal to, well, by definition, this is VA dF, right? But this is very similar to what we had before. So this is equal to VA, and then we should have the A component of the F. So indeed, if you take the f, the components we should have of the f are exactly the correct ones. It should be these gradients. So what happens now if we take the derivatives, the differentials of the coordinate functions? So I call them YA. So any coordinate function is a function on the space, right? That's the definition of a coordinate, is having enough independent functions that you can uniquely identify a point in your space. But at each point, every coordinate function takes a value, so it's indeed a function. So we can write down the differentials here. So the YA, and we can ask ourselves, when we act on a vector v using the YA, what is this? Well, it's by the same argumentation here, it's by definition v, and then, well, let me write out everything. dBya. That's just writing out the definition, right? But this thing here, I mean, let me write out what this term actually is. It's the partial derivative of YA with respect to YB. And since the coordinate functions are independent, it's actually equal to delta AB. So this is VB delta AB, so this is equal to VA. Okay? So, in other words, if I define now W to be a linear combination of, sorry, I should use the index down here, as a linear combination of these coordinate differentials, then if I take W of V, then this by definition should be WA dYA acting on V, which is just VA WA. So indeed you get exactly the correct thing. It's exactly what we should get. We should get exactly this thing, right? So indeed these coordinate differentials are exactly the basis components that we're after. So we can define here that EA is this coordinate differential dYA. So these differentials are indeed the basis of the dual space, or we can take them as the basis of the dual space. So, I mean, compare this to what we had in the Euclidean case. So we had the gradient of the coordinate functions. In the same way, we have here the differentials of the coordinate functions. In the same way as for the tangent vectors, for the tangent basis in Euclidean space, we have the partial differential of the position vector. In the tangent, in the general case, we have that we define the tangent vectors as just the partial partial derivative. So we have kind of the same structure as we did in the Euclidean case. Okay, any questions? If not, let me take just an example here. So an actual physics example. I'll not discuss it in very long, but I want to stress the fact that we don't necessarily have an inner product here. But you've probably seen something like this if you had a thermodynamics course. du TdS minus P dV, right? So this is the differential of the internal energy. Can be expressed as temperature, which is a function on thermodynamic state space, times ds, where S is entropy, minus the pressure times dV, where V is volume and P is pressure. So this is exactly, here we are using on thermodynamic state space, we here use S and V as coordinates. But there is no a priori metric on thermodynamic state space, but you can still compute things like the change in internal energy. For example, if you had an isentropic process, then along that path in thermodynamic state space, you can find out how the internal energy changes along that path. And it's only going to be, if you go in with an isentropic process, then the S is going to be equal to 0 along that path, and it's just going to be given by minus P dV. I mean, I don't know about you personally, but I always found thermodynamics a bit wiggly until I actually realized that what was going on with these differentials. It's actually this that is going on. It's the thermodynamic state space is a general manifold without necessarily a metric, and you can describe using different state functions. You use as different coordinates on that state space. Okay. So now that we have defined the tangent vectors and we have defined the dual vectors, let's just discuss a little bit about how to relate these in different spaces. So that's going to be useful when we later on are going to discuss derivatives. So the basic problem here is this, right? That when we define a derivative, typically, we want to take the difference between a vector here, let's say, and a vector, so derivatives of vectors now, and a vector in a point which is not really that point, but a point that is very close to that point. But in general, as I said, in two different points, you have different tangent spaces. So it's not clear how you can actually define a difference between a vector in this point and a vector in this point. So it's not clear how you can take the limit of that when the points come closer. So in order to do that, we'll first have to go through a bit of general definitions regarding what is called pushforwards and pullbacks. And then we'll see how we can use this to define the derivatives. So pushforwards and pullbacks. So let's consider the following. A function that goes from one space to another, and I just call them M and N here. So we have some space M, and we have another space N, and we have a function going from M to N. Okay? Now, if we have a curve in M, so let's call this curve gamma, then we are naturally going to have a corresponding curve in the other space N here. So we can, so a curve in M, so that's essentially a function from real numbers to m, right? A curve here is a function from real numbers to m, essentially with a curve parameter as the real number. So if I give you a curve parameter, you map to a particular point. If I give you a larger curve parameter, maybe I map to a point later at the curve, in the curve. So such a curve also with this function f defines a curve in n, which is called the push forward f gamma. That is a function from r to n that is given by just the composition of these two. So gamma composed by f. So that means that if I take a real number, I map it to a point in m, and then I use f to map that to a point in n. And then I'll get some different curve. I don't know how it looks. Generally, that depends on f, but I will have some different curve in n. Right? But that also means that if I take a point P here in M, that's going to map to some point F of P in N. This curve gamma is going to have a tangent vector here that I can call gamma dot. But the corresponding curve in N is also going to have a tangent vector. And I'm going to call that the push forward of the tangent vector of this gamma dot. So in essence, what this means, let's relate those to each other. So if I take f star gamma dot and I act on some function phi here, so phi is a function here that lives in n, so phi is a function from n to real numbers. Since the push forward of gamma dot is a vector in n, it's a tangent vector in n, it's a direction derivative in n, so I should be able to act on this function. So this is going to be the time derivative of the full composed function, or the derivative with respect to the curve parameter of that function. So this should be equal to gamma dot of the composition here. So what do I have is phi composed with f. Okay, because this here, f is a function from m to n, so all of this is a function from m to real numbers, right? So therefore I can use gamma dot, which was a vector living here, to take a partial derivative of that function. Okay, but by definition, by definition, if we use coordinates now, y on m, this is y dot a dA acting on this composed function. But by the chain rule of derivatives, this is y dot a and d, and let me now use barred coordinates for n. dya, and then d bar a acting on phi. Okay, so this is just the again the chain rule of derivatives, because we have a composed function here. And just to make that clear, I am using now coordinates ya on m, and I'm using barred coordinates to refer to coordinates on n. And also, of course, the barred derivative here is a partial derivative with respect to the barred coordinates. So what is here in front, that's y bar dot b, right? That's exactly what it should be. It's the component of the tangent of this vector. Okay, so that's the push forward of a tangent vector. So if I have a vector here, I can push that forward to here, and I get a new vector in n. I get a tangent vector in n. By a similar argumentation, we can continue. So for a dual vector, so let's call it omega. Let's take a dual vector now in n, f of p n. Okay, so this means I have a dual vector living in this point. So I'm going to be able to naturally relate that to a dual vector in M at the point P. And the way to do that, so we define the pullback by F of omega as, now I put the star up, the pullback of F omega, that's now a linear, it should be a linear map from vectors living in M to real numbers. So I can take a vector V living in M, but I define this as omega acting on the push forward of V. So given that I have a vector V in M, I can relate that to a vector, the push forward vector in N, on which I can apply the dual vector omega. And I simply define the corresponding pullback of omega to M by this relation. And you can verify that this is indeed going to be linear as well. Okay, so in general, of course, if F is invertible, so let's assume that we can invert F, then we can use then we can use F inverse to pull dual vectors from here to there, and the vice versa. We can use F inverse to push tangent vectors from N to M. So if F is invertible, then we can relate any dual vector living any dual vector or tangent vector living in M to a dual or tangent vector living in N. Any questions? Yeah, so the push forward, let's see. The question is, where do I define the push forward? So the push forward is defined as the tangent vector. So the curve here has a tangent vector which is gamma dot, and given the tangent vector, you can always find the curve such that it is the tangent of that curve. And that means that I get a different curve in N. So So given the tangent vector, I can pick a curve that has that as the tangent. Then I map that curve to n using the function f. And I define the push forward of this vector to be the tangent vector of that curve, which I have in n now. Does that make sense? Yeah. Okay, so let me just mention before the break that that if we have this inverse, then of course if f inverse, so that's the identity. So if we have this, well, it's true whether or not the star is up or down. So if I have something that lives here, I push it forward using f, and then I push it back using f inverse, I get back the same vector. And you can check relatively easily that that is indeed the case. And we can generalize this, of course, to arbitrary tensors. When we take tensor products of tangent and dual vectors, we can generalize this to be true for any type of tensor. In order to be able to push forward a mixed tensor, so a tensor product of a tangent vector and a dual vector, you need f inverse to do that. Since you need to go from here to there for a tangent vector, you use f, and to go from here to there for a dual vector, you use f inverse. Okay, it's 18 past, so let's begin again. During the break, I just took the liberty of writing down what we said just before the break explicitly. So just that we define the push forward of gamma dot here as the tangent of the push forward of gamma. So we had this curve in M that was pushed forward to N, and then we define the push forward of the tangent vector in M as the tangent of the curve that was pushed forward to N. Okay. So let's go on. So we are now equipped with enough tools to define what is called the Lie derivative. So to do that, I want you to first have this mental image that we had before the break, remembering that if you have two different tangent spaces, no matter how close, so I can move this P very close to Q, no matter how close the tangent spaces are, you can't necessarily add and subtract vectors from different tangent spaces. So the typical thing you would like to do when you define a derivative is the following. So the typical, let's put that in quotations, derivative would be that if you have some function f, but let's take a vector instead. So if you have some vector field, you would like to take it at point x plus epsilon times some direction you want to take the derivative in, minus b of x, and you want to divide that by epsilon, and you want to take the limit of epsilon going to 0. So in the general space, this fails because this vector and this vector, they don't live in the same tangent space. So even if I'm close here to Q, I'm not living in the same tangent space. So I cannot construct this vector difference. So I can't take the limit either. So the Lie derivative kind of helps with that in the following way. So let me define what is called the flow. The flow of vector field. A vector field V is a map. I'm not going to call it gamma. Gamma v. V, the subindex referring to the vector field. And it's a map from a real number and M to the space M itself. So if you think about it, if you fix this argument, then it's a map from R to M, so that's a curve. If you fix this argument, then it's a map from the manifold to itself. Then it's the kind of object that we had for F here before the break. Then it's one of these types of objects, just M being equal to N. Okay. But that's not enough. That satisfies a couple of conditions. First of all, gamma v of 0 and some point P in M, that should be equal to the same point P again. This is an initial condition for these curves. So if I take here to put the real number to 0, I should have the identity map. It's a map from M to M, that is the identity map. So that's the first requirement. And then in addition, I want to have it for fixed P. I can take the tangent vector here. So gamma dot V of S and P should be equal to V evaluated at P, evaluated at gamma V SP. So this is essentially saying that wherever you look, the tangent of this flow is the vector field V. So you can imagine here, if I have just draw generally M, I draw some vector field. Let's not draw too many arrows. So if I take P here, I take a point P, then the flow here is a curve that at each point along P has the vector field V as its tangent. Okay, and I can choose different points here. I can choose Q, for example, and I will get another curve, but that curve still has the vector field V as the tangent. Okay, so this is called the flow of V. Okay, that's good. I want you to note now that for a fixed S, gamma V of SP is a map from M to M. So that means that we're going to be able to use this as this kind of function where N is now the same space again. It's M. So I'm going to be able to use this to make pullbacks and pushforwards within M itself. And you should also notice that these conditions actually make this an invertible map. So invertible is important as well. Okay, so that means that given this this flow, if I have a vector along the flow line, then I can relate that. I can make the pullback to the original point, to Q in this case, or I can take this and I can pull it back to P. Okay? So we define here, let's define, just for shortness of notation, we define gamma SV for some fixed S of P. That's a map from M to M as gamma SV of P is just this gamma V of S and P. So it's the flow with the curve parameter being equal to S. Okay? But this means here that the pullback of this vector using this is a well-defined thing. So I can take this vector and I can use the pullback to get a vector here. Or I can take any vector rather here and then get a different pullback here. So what this means is the following. So given a vector field X now, so let me redraw a picture here. I have some vector field V that defined essentially how my curves look, here. And then I can have an additional vector field X. So X can look a bit like this. We don't really know how X looks. Doesn't matter. So at each of these points, we can draw curves essentially that are that X are tangent of. And using this pullback, I can take these vectors here, this X and this X. I can use the pullback to pull them back to the original point. That's essentially taking this curve and pulling it back to a different curve here. Or this curve, and pulling it back to a different curve here. That's going to define a different X. So this would be gamma SV X. This now would be the pullback of, say, that vector, if the parameter is S there. That is not necessarily the same thing as that vector. So we define now the Lie derivative. Yeah, sure. Sorry, there was noise in the background. So it's in order to be able to, well, in this case, I want to have a vector, given a vector here. I somehow want to create a difference vector of vectors here. So I have this original vector, X. I want to somehow compare it to a vector that is in a different place. And I can do that if I have a pullback, in this case. If I can pull this vector back to that point, I can take the difference, right? Because now it is vectors at the same point. So this is exactly what I'm going to do now. So I'm going to define the Lie derivative in the direction of V of the field X. So if you look back to this typical thing that we can't do now, I wanted to have a vector at a different point, subtract the vector at the point I'm interested in, and then divide by epsilon. This is exactly the same thing that I'm going to do now, except that I now have a vector that depends on the vector at this different point that I take back to the point where I'm interested in defining this Lie derivative. So I'm going to define this as the limit of S going to 0 of this pullback of x minus x, and then dividing by s. So this is now an object that depends on the vector at this point, that some is displaced by some vector v in some direction. I get that vector and I pull that back to the original point, and there I can take the difference between those two vectors. So the entire idea here is that I can use this to define a derivative of a vector field or a general tensor field. There's nothing here that says that x necessarily needs to be a vector. It can also be a tensor field. And the definition is exactly the same. That you pull the tensor back from a point that is displaced by v, and then you take the difference at the original point. Okay, so let's take an example here, or a couple of examples, because it becomes a bit abstract. Well, first of all, if we take a scalar field is a rank 0 tensor, right? So for a scalar field, to have this make some sort of sense, we would like to recover the direction derivative of a scalar field, right? So let's check that the lead derivative of a scalar field phi actually fulfills this. So I'm going to evaluate this at some point p. So by definition, this is the limit as s goes to 0 of gamma sv of phi evaluated at p minus phi evaluated at p divided by s. But if we check what this actually is, limit of s goes to 0, so we're going to have small displacements. So this would be the value of phi at gamma v of s and p minus phi at p divided by s. So assuming now that s is small, which is going to be in the limit, then we're going to have the limit of s going to 0 of phi, and I now write the coordinates. So the coordinates ya plus s va. So this is by definition of the flow, right? So I should have the tangent vector v at every point, minus phi at the point itself, so that has coordinate ya, divided by s, but this is just, again, the same limit. It's phi of ya plus s va dA acting on phi minus phi of ya, everything divided by s. You see that these cancel just as they would for a normal derivative, and the s's cancel, and what we are left with is va dA phi, which is exactly this direction derivative of the scalar field. So that's fine. Let's do something a little bit more involved. Let's take the vector field and try to figure out what the lead derivative of a vector field is. So I want to have the lead derivative in the direction of v, which is a vector field, over the vector field x. So exactly the same thing we tried to do here. I want to evaluate this as p, and let's take the a component of that. So this, by definition, then would be the limit as s goes to 0, and then I should have 1 over s, and I have the pullback here of x evaluated at AP minus x evaluated at P. So I need to figure out what this object is. Okay, so let's try to do that first. Let's take this object, gamma SV of x. And evaluate that at y, at the point at coordinates y. So by definition, by what we saw before with the break here, this is going to be the vector component xa at the new point y bar times the derivative at the new point, right? But this is xa, and then we have at the point then y plus sv, right? Because this is the new point when s is small. And then we use the chain rule, so dyb, the y bar a, db. Okay, so the question is essentially, what is this object and what is this object? This is just a function, so I'm going to be able to do the same thing I did here for the scalar field. I'm going to express this as a Taylor series. So this would be xa at the point y plus sv, so that's x at y plus the derivative now, svb db of xa. That's the first term here. And the second term here, I need to use here the fact that if I know that y bar a, that's ya plus sva essentially, right? So I can take the v to the other side, and that makes ya equal to y bar a minus sva. And if I differentiate both sides here, I get, with respect to db, I get delta ab plus equal to actually, do I need to I differentiate with respect to the barred components, right? So I get sorry, don't get that on the right. I differentiate, it's this derivative that I want, right? So if I take, let's use the correct, let's use the correct indices here. Let's use b here. And I differentiate with respect to y bar a. That means that I have this dyb, dy bar a, and then I have delta ba from the first term, minus s was a fixed number, d bar a vb. But to leading order, which is the only thing that's going to survive here, this derivative is the same as the derivative dA. So I'm going to just approximate this by delta BA minus S dA VB. So that's the second thing I have here. I have delta BA. So B was a bad index here because I had B in some other terms. Let me use C instead. And delta BA minus S dA VB dB. Okay, So keeping just the linear terms here, well, the first leading term is XA delta BA dB. So that's just XA dA, right? But then I have two more terms. I have linear terms which go with S. The first one is VC DC XA. And the second term has a minus sign, minus XA DA VB, and we are missing there should be a dB here because I had a B from the delta. So this delta going with that one makes this A into a B. And then dB. Of course, once I have this, I can rename these indices A again because I have no A's in these terms. So this here is what is called the commutator, or it's a component of the commutator of the vector fields. So this is, by definition, the component of the B component of the commutator of vector fields. So this is exactly what we'll have. So this term here is going to cancel this term. And we're going to be left with the linear term. The S is going to cancel that S. And what we'll be left with here is Vx A component at P. Where this commutator is exactly this commutator. Let's just note also that if we act with this, so this is a vector, right? So if we act with this on F, that's the same thing as acting, as taking the difference of first acting on F with X, which gives you a new function that you can act on with FV, and taking the difference of that with doing the opposite. So X acting on V of F. Okay. So that's the vector field. Let me just mention the 0-2 tensor. So let me write a general 0-2 tensor with indices A and B. Just lives in the tensor product space of dual vectors tensored with each other. So this would be T star P M cross T star P M, right? In that space. So this has covariant components with two indices. If we do this, then the Lie derivative of T, the AB components of that, are going to be given by VA or VC DC TAB plus TAC DB VC plus TCB DA VC. And this follows from exactly the same kind of argument that we did for the vector field, but I just wanted to write this down so we have it. Big difference is the plus appearing here instead of the minus that appeared here for the vector fields. This is because we have a dual vector, or a dual tensor rather than a tangent. Okay. Okay, so I want to go on to define what is called an affine connection now, which is a different type of derivative. And the reason I'm going to define this is that we want to have sort of a tensor derivative that when acting on a vector field or a general tensor field, satisfies a number of properties. And it turns out that the Lie derivative, while useful in many senses, is not going to satisfy. So there are a number of properties that we would like a directional derivative to satisfy. A directional derivative would ideally satisfy the following. And you can check that your typical directional derivative in Euclidean space does satisfy this. So first of all, let's call it gamma, nabla v. This being the directional derivative in the direction of v. So first of all, I would like that when you act with this directional derivative on a scalar field, it should reduce to just being the vector field as a directional derivative acting on f. Okay? So when f is a scalar field. So this is a reasonable assumption. Second, I would like it to be linear in the direction. This is actually second and third. So what does linear in the direction means? Well, it means that if I take x plus y and I act on some tensor t, I want that to be the same as acting in the direction x on t plus acting in the direction y on t. So I want my derivative to be linear in the direction. But I also want that when I multiply the vector, the direction by some constant or by some number, some function f, and I act on a tensor t, this should just multiply the entire derivative by f. So I should get that. So these are linear in the direction. And note here that this should hold true even if f is not a constant. So for example, if I multiply the vector field, the vector direction in which I want to take the derivative by a number that depends on the position, I should still just multiply the derivative by that function. And finally, the fourth requirement is that if I should satisfy the product rule of derivatives. So if I take the product of tensors t and s, what I should get out of that is just the product rule. So the derivative acting on t times s plus t times the derivative acting on s. This is just the product rule. And you can verify that the Lie derivative satisfies 1, it satisfies 2, it satisfies 4, but it does not satisfy 3. In particular, if we take the Lie derivative, so let's take LFV acting on x, when v and x are tensor fields, this would be FVX, and that is indeed FVX, but there is an additional term which is minus XFV. So this term actually breaks this third requirement. So the Lie derivative is not an affine connection because it does not allow this type of linearity. Okay, so what can we do? Well, in general, let's just assume that we have a derivative that satisfies this. So assume an affine connection satisfying the above. Then for any vector W, vector field W and vector V at some point, we know that nabla V acting on W should satisfy these things, so we can use these requirements now, these 4 requirements, to rewrite this. So first of all, let me expand V and W in components. So this would be VA, DA, WB, DB. But I know that this affine connection is linear in the direction. So this, I can take the VAs out. I get nabla DA left acting on WB DB. And that's just using the linear property here. And this thing, I'm just going to define a shorthand for that, just not to have 2 small notations. So I'm just not going to write out the partial derivative. I'm just going to call it nabla A. Okay. But then I can use this property, and I can use this property. So let's see what this becomes. So the product rule, I have VA, and then I have essentially what is nabla A WB DB plus let's see here, we should have WB nabla A DB, right? Okay. WB, that's a scalar function. It's a component of the vector field W, but WB in itself is a scalar function. So this thing here is dA WB. This thing here, I don't know what it is, but I know that it should be a vector. So I can expand this. I can define this as gamma AB, and then some component C DC. That's a general vector being written down in terms of the basis, depending on A and B, right? So I don't have any more space here. Let's move on to the next page. So this is what I had. So if I write this down, I have VA, and then I have DA WB DB plus WB gamma ABC DC. I'm going to use my liberty to rename indices. So I'm going to switch places of B and C here, because when I do, that means that I can take this partial derivative dB out, and I can rewrite this as VA dA WB plus gamma ACB WC dB. So you might recognize this from Julia's lectures. This is actually what you were calling the covariant derivative, right? It's just that these gammas I have not defined yet, and I don't necessarily need to define them using a metric. I can define them as whatever I want, and I will satisfy these rules. So a particular choice, so any particular choice of connection coefficients gamma CAB defines an affine connection. And in particular, if you have a metric, you will be able to define a particular affine connection, which is called the Levi-Civita connection, where these gammas become the Christoffel symbols. Any questions? So this is a general affine connection. Okay, we don't have much. I had hoped to reach a discussion on symmetries. We'll have to postpone that to next time. I just want to say a little bit about what is called geodesics. So in a metric space, you would typically define a geodesic as a path minimizing the distance between 2 points. However, in a general space where you don't have a metric, so even if you don't have a metric, there is no metric. We can define a geodesic using an affine connection. So we say that a curve gamma is a geodesic if the derivative of the tangent of gamma along gamma, so in the direction of gamma, is equal to 0. So what this is saying is that you have the directional derivative in the direction of the curve of the curve tangent is equal to 0. Then we say that this is a geodesic. So it's a curve whose tangent doesn't change for the purposes of defining change using the affine connection. With that definition, the tangent doesn't change along the curve. So that's our definition of geodesics. And if we use the Levi-Civita connection, this actually agrees with the definition of geodesics as the path minimizing the curve length.